Imagine you're driving 70 miles per hour down the highway. The weather's clear, the road is open, and everything feels, perfectly under control.
Right.
But in a fraction of a second, deep inside the chassis of your electric vehicle, the computer controlling your battery pack decides it. It no longer speaks the exact same language as the computer controlling your wheels.
Which is a terrifying thought.
It really is. I mean, if they were human, one of them would just pause and say, hey, what did you mean by that?
Exactly. They'd ask for clarification.
Right, but these are computers. They operate in microseconds. And without the invisible, deeply complex digital safety nets we are about to uncover today, that minor translation error would instantly lock up a 2-ton vehicle traveling at highway speeds.
It's the absolute definition of a high-stakes environment. I mean, we're no longer living in a world where a software glitch just means, your web browser crashes and you have to restart your laptop.
Yeah, you just lose your tabs.
Right. When millions of lines of code meet thousands of pounds of moving metal, the margin for error effectively becomes zero.
And that is exactly what we are unpacking for you today. Welcome to the deep dive. We are looking at a highly technical, incredibly high-stakes engineering document. It's a functional safety and fault diagnostic technical specification for hybrid dual-motor power control systems.
It's quite a mouthful.
It is, yeah. But specifically, we are focusing entirely on one critical, terrifying failure mode. In the industry, it's known as D08 firmware version mismatch.
Which, it sounds completely mundane. Firmware version mismatch.
Right. It sounds like you just forgot to update your phone overnight or something.
Exactly. But in the context of an electric vehicle's powertrain, it is a catastrophic event waiting to happen.
So the mission here is to decode exactly how modern EVs prevent that catastrophe. How do they stop a motor from suddenly accelerating out of control or, exploding its internal components just because of incompatible software?
And they really do go to extreme lengths to prevent this.
They do. We're going to rip this system apart from the inside out. We're looking at the root causes of how these mismatches happen, the architectural defenses built right into the code, the design strategies meant to prevent them before the car is even built, the strict controls on the factory floor, and finally, the absolute torture testing these components endure before they ever make it into your driveway.
Because the reality is, if you own a modern car, you own a rolling supercomputer.
Yeah.
And understanding how that computer protects you when the physics get extreme is crucial.
Okay, let's unpack this. Let's start at the very top of the risk ladder. What actually happens when this simple mismatch occurs in the vehicle?
Well, when things go wrong here, they trigger a very specific diagnostic trouble code in the car's brain, which is DTC U0311.
U0311, okay.
Right, and that translates to Drive Motor Control Module Software Incompatible. Now, in the world of automotive safety engineering, there's this strict international standard called ISO 26262.
Right, I've seen that referenced.
Yeah, it ranks the severity of potential hazards from ASIL A, which is, relatively minor, all the way up to ASIL D.
And let me guess, this is ASIL D.
It is ASIL. That is the highest red alert there is.
Wow.
An ASIL D classification means that if this failure occurs, it has the potential to lead to severe, life-threatening injuries or even fatal accidents, with absolutely no time for the driver to react and save themselves.
So the stakes literally could not be higher. But, why is a version mismatch so deadly? My laptop has mismatched software versions all the time, and the worst that happens is my printer stops working.
Because your laptop isn't orchestrating massive amounts of raw, high-voltage electricity across multiple physical systems simultaneously.
Fair point.
In a hybrid dual-motor EV, you don't just have one brain. You have a massive interconnected nervous system. You have the vehicle control unit, the VCU, which is essentially the conscious brain deciding what the entire car should do based on your foot on the pedal.
Okay, so that's the boss.
Right. Then you have the battery management system, the BMS, which is intensely monitoring the chemistry and temperature of the energy source. And finally, you have the power control system, the PCS, which acts as the muscles. It's the system firing the electricity into the physical motors.
So they all have to be perfectly synced up.
Exactly. If the software versions, the physical calibration parameters, or the communication dictionaries between these three massive modules don't perfectly align.
And down to the exact bit.
Down to the exact bit, yes. The system could literally lose control of the motors.
Which brings us to the real question here. How does that misalignment actually happen in the real world? The source document outlines 4 distinct physical dimensions for these root causes. And what strikes me immediately is that these aren't just coding errors.
No, they're not.
They're moments where the physical reality of the car actively sabotages the digital software. The first one is called low voltage power sag and torn rights.
This is a beautiful but terrifying example of physics interrupting digital intent. Imagine your car is parked in your garage. You tapped Update Now on your app, and the car is doing an over-the-air firmware update.
Right, the progress bar is moving.
Exactly. It's writing megabytes of brand new code into the microcontroller's flash memory. But writing to flash memory requires a highly stable, continuous flow of voltage.
Yeah.
And right in the middle of this critical writing window, the car's 12-volt battery experiences a sudden, massive drop in power.
Wait, hold on. Electric vehicles have massive 800-volt battery packs that weigh 1,000 pounds. Why are we talking about a little 12-volt battery?
Because the 800-volt battery is exclusively for propulsion. It's just for moving the heavy car.
Oh, really?
Yeah, the computers, the screens, the lights, and the microcontrollers are all still powered by a standard 12-volt system, just like in a gas car. And that 12-volt system is a massive bottleneck.
I had no idea.
So let's say during the update, a heavy-duty thermal coolant pump suddenly kicks on to keep the main battery pack warm, or a massive high-voltage relay clicks shut. That sudden draw of current causes the 12-volt supply to sag for just a fraction of a second.
Like a brownout in a house.
Exactly. It's a brownout. The voltage supplying the microcontroller unit falls below a critical operating threshold.
So it's like trying to write a crucial, incredibly detailed letter with a fountain pen, but while you are writing, someone actively dims the lights in the room and someone else slowly pulls the paper away from you.
That's a great way to picture it.
Like, you're still making the motions, the ink is still hitting the page, but when the lights come back up, the word you were writing is incomplete. The ink is there, but it doesn't make any sense.
That is the exact mechanism, but we really need to look at it at the microscopic level to understand why it's so destructive.
Okay, let's zoom in.
The flash memory inside these controllers doesn't store data on magnetic tape or spinning disks. It stores data by literally trapping electrons inside something called a floating gate transistor.
Trapping electrons.
Yeah, it uses physical electrical voltage to push electrons through a microscopic insulating barrier and lock them into a tiny cage.
So writing software is actually moving physical particles.
Yes, and if the voltage sags, you lose the push. The storage cells don't get fully saturated with the electrical charge. On the surface, the computer thinks the write operation completed, but physically there's only a partial charge trapped in the cell.
And that's a torn right.
Exactly. Now, when the computer reboots and tries to read that memory, it uses an internal mechanism called error correction code, or ECC. Think of ECC as a hardware-level spell checker.
Okay, so it fixes typos.
Right. If a single electron slipped out of place, creating a single-bit error, ECC can fix it on the fly. It's incredibly robust. But a torn write doesn't create a single-bit error. It leaves a massive jagged crater of multi-bit errors across the memory block.
So the spell checker looks at the word and just throws its hands up.
Right. The ECC flags it as an uncorrectable error. The memory is fundamentally corrupted, and if the processor tries to execute that partially written code to drive the car, the entire system will crash.
That is wild. A tiny dip in a 12-volt battery basically shreds the software at the electron level.
Yep.
Okay, let's look at the second root cause. The document calls it hardware-software parameter mismatch. And this one seems far more, I don't know, human. This happens during maintenance, right?
Yes, and this is where we see how incredibly specific EV software has to be. Controlling a dual-motor electric vehicle isn't just generic math that works on any motor.
Right.
It relies heavily on precise physical calibration that is unique to the exact specific hardware physically bolted into that exact car.
Because no two motors are perfectly identical, right?
Right.
Even if they roll off the same assembly line, at the atomic level, the magnets and the copper coils are going to have slight microscopic variations.
Precisely. Now, imagine a mechanic in a service center is working on your car. They replace a faulty motor, or maybe they just replace a sensor called a resolver.
What does the resolver do?
It's the sensor that measures the exact rotational angle of the motor shaft. So they bolt the shiny new hardware in, plug in the cables, and it looks perfect. But they forget to run a critical software routine on their diagnostic laptop called commutation offset learning.
Oh, no.
Or perhaps even worse, someone at the factory accidentally flashes a generic default set of parameters into the controller instead of the custom parameters measured for that specific car.
So the brain, the software, thinks it is talking to motor A with motor A's exact quirks and magnetic alignments. But motor B is actually what's bolted into the chassis. What is the physical consequence of that?
To understand the danger, you have to understand the physics of how these motors actually generate movement. They use a technique called field-oriented control, or FOC.
FOC. Okay.
Imagine the motor has two main parts. You have the stationary outside part, the stator, which is wrapped in copper wire, and the spinning inside part, the rotor, which is covered in powerful permanent magnets.
Okay, stator stays still, rotor rotates. I can remember that.
Right. The controller's job is to shoot electricity into the stator's copper coils to create a magnetic field.
Hmm.
But it doesn't just create a static field. It constantly shifts the electricity to create a spinning magnetic field.
Oh, okay.
The permanent magnets on the rotor are basically chasing this spinning field, and that's what turns the wheels. But to do this efficiently, the controller needs to know the exact microdegree angle of the rotor at all times.
It's all about timing. It makes me think of like pushing a child on a playground swing. You have to push at the exact right moment, right as they reach the peak of the backswing, to transfer the energy efficiently and make them go higher.
That is a brilliant analogy. Yeah. Now, what happens if your commutation offset is wrong? It's like pushing that swing with all your strength, but your timing is wrong, and you push while the swing is coming aggressively right at your face.
Oh.
Yeah. According to the technical specification, if that parameter mismatch causes the FOC angle to be off by more than 45 degrees, you get a catastrophic physical reaction. The moment the controller tries to start the motor, it pulls a massive, violently unconstrained wave of current from the battery. It's called direct access overcurrent.
Unconstrained current, meaning way more electricity than the physical wires are designed to handle.
Yes. It is a massive thermal spike.
Yeah.
Inside the motor controller, the power is handled by these incredibly advanced microchips called silicon carbide, or 58 power modules.
Yeah, the Suki modules.
They're designed to handle hundreds of amps of current efficiently, but they're still physical materials. When that direct access overcurrent hits them because of a 45-degree software timing error, the thermal shock destroys the silicon carbide in milliseconds. They literally blow up.
Unbelievable. From a forgotten calibration click on a mechanic's laptop to exploding silicon carbide inside a metal box. Software mistakes causing literal shrapnel.
It's a harsh reality.
Okay, let's move to the third dimension of these root causes, which is communication database drift. This one deals with how the different computers in the car actually speak to each other, right?
Yes. Modern EVs are essentially rolling networks. They use a protocol called NNFD, which stands for Controller Area Network Flexible Data Rate.
Flexible data rate. Okay, got it.
Think of CAN-FD as a highly structured, ultra-fast group chat between the VCU, the BMS, and the PCS. They communicate constantly, sending thousands of messages a second.
Wow, that's a lot of chatter.
It is. But a computer doesn't send the English sentence, limit power to 10%. It sends a string of ones and zeros. To understand what those ones and zeros mean, every computer on the network uses specific matrices, essentially shared dictionaries, like DBC or ARXML files.
So they have to have the exact same dictionary.
Exactly. These files strictly define exactly what each bit of data means in a given sequence.
But here's the rub, right? These different modules, the battery brain, the motor brain, they are often built by different suppliers, or they evolve independently, they get different software updates at different times.
And that is exactly where the drift happens. What is deeply fascinating here is how incredibly fragile that shared dictionary is in binary code. Let's say the vehicle control unit gets an update, but the power control system doesn't.
Okay.
We experience what engineers call a version slide. A single data field in the dictionary gets shifted by just one bit, or the length of a specific message changes slightly in the new version.
So the dictionaries are out of sync. Give me an example of what that actually looks like when they try to talk.
Let's use binary math. In binary, the position of a 1 changes its entire value. Let's say the VCU wants to send a completely benign, safe command. It wants to say, the battery is a bit cold, so limit the power output to a value of 2.
Okay.
In binary, a 2 might look like 0010.
Okay, 0010 goes across the wire.
Exactly. But the power control system on the receiving end has an out-of-sync dictionary. Its dictionary says that the data field starts 1 bit earlier than it used to.
Oh.
So it reads that exact same signal, but shifted. Instead of seeing 0010, it shifts the frame and reads 0100.
And what is that?
In binary, 0100 isn't a 2, it's an 8.
Oh, wow. It completely changes the mathematical reality of the command.
Yes. So the vehicle control unit sends a safe, limited power command. The motor controller receives a perfectly intact signal, unpacks it using the wrong dictionary, and misinterprets that low limit as a command for maximum extreme torque.
That is terrifying, because the computer doesn't know it's making a mistake. It thinks it is perfectly executing a valid command.
Precisely. It acts on the corrupted reality it was handed. This is why a communication drift must instantly trigger the U031 fault. The systems must be speaking the exact same dialect of the exact same language down to the absolute final bit, or the car becomes a dangerously unpredictable weapon.
Okay, the fourth and final root cause dimension from the spec sheet is secure boot failure. And I have to admit, this is my favorite one because the engineering document explicitly mentions cosmic rays.
It does, and it's not science fiction. It is a daily reality for aerospace and automotive engineers. We have to account for something called single event upsets.
Single event upsets.
Yeah, our atmosphere is constantly bombarded by high-energy neutrons originating from cosmic rays outside our solar system. If one of those neutrons happens to strike the microscopic silicon of a microchip at exactly the right angle and speed, its physical energy can actually flip a single bit of memory from a 0 to a 1.
Just a rogue particle from a dying star billions of light years away deciding to mess with my morning commute. That is nuts.
It is. I mean, it's statistically rare for a specific bit, but across millions of cars over years of driving, it is an absolute certainty. But it's not just space weather. More commonly, high-temperature aging over years of driving can cause the silicon to degrade and flip bits on its own. Or, in a more malicious scenario, a hacker or a third-party tuning shop might try to forcibly flash unauthorized, unverified software into the car to unlock more horsepower or bypass safety limits.
Right, trying to jailbreak the EV.
Yes. Now, if the system's bootloader, which is the very first deeply embedded piece of code that wakes up when you press the power button, if that lacks strict hardware-level cryptographic checks, it has no way of knowing the code has been altered by a cosmic ray or a hacker.
It just blindly trusts it.
Exactly. It just blindly loads that corrupted or unauthorized software into the main processor.
And what happens when that bad code actually runs?
It's disastrous. When that corrupted code tries to execute complex, timing-critical driving maneuvers, it will inevitably hit a mathematical wall and crash. This causes what we call a watchdog reset.
A watchdog reset.
Yeah, the computer's internal safety monitor panics because the system froze, and it completely cuts power and forcibly restarts the entire computer.
While you were driving.
While you were driving, you would lose all power, all screens would go black, and you would lose all drive control while the computer desperately tries to reboot itself.
Which is the absolute nightmare scenario we have to avoid. So to recap the threats, we have 12-volt power sags causing partial writes at the electron level. We have mechanics forgetting to calibrate the precise physical angle of the magnets, leading to exploding chips. We have dictionaries drifting out of sync and turning limit power into max throttle. And we have cosmic rays and hackers altering the fundamental code.
Those are the four physical realities constantly trying to tear the software apart.
Which brings us to the defense. We are moving from the root causes to the technical architecture and co-diagnostics, the digital fortress. Because the car isn't just a passive victim here. The engineering requirement laid out in this document is absolute, isn't it?
It is uncompromising. The specification states the system must catch this version mismatch 100% of the time at startup. And if the mismatch somehow occurs while driving, say, due to a severe hardware fault, it must detect it within 50 milliseconds.
50 milliseconds? That's what, a 20th of a second?
It is about how long it takes a hummingbird to flap its wings a single time.
That's incredibly fast.
That is the entire window the car's architecture has to detect a fault, analyze it, and execute a safety protocol to save your life. To achieve that impossible speed, the architecture utilizes what we call a long-depth defense system.
Okay, long-depth defense.
Right. It is not one single barrier. It is a series of 4 progressively deeper interconnected layers of defense.
Let's walk through this fortress. Layer 1 is the HSM secure boot. You mentioned hackers and cosmic rays earlier. How does this first layer stop them?
By fundamentally mistrusting everything. The microprocessors used in these critical systems, like the AURX TC3XX family, are not just normal single-core computers. Built physically into the silicon is a completely separate, highly isolated coprocessor called a hardware security module, or HSM.
So it's literally a computer inside the computer.
Think of it like an incredibly strict bouncer standing outside the main club. When you turn the car on, before the main central processing unit is even allowed to look at the application software that runs the motor, the HSM wakes up first.
Okay.
It takes complete control of the memory bus. It uses a dedicated physical hardware acceleration engine to run a highly complex cryptographic algorithm specifically SHA-256, across the entire multi-megabyte block of flash memory.
Okay, I've heard of SHA-256 in cryptography and blockchain. It calculates a hash, right? Like a digital fingerprint.
Exactly. But it's a mathematical one-way function. It reads every single 1 and 0 in the code and produces a unique string of 64 characters. If even a single comma is changed in the source code, or if a cosmic ray flips one single bit out of millions, the resulting 64-character hash will look completely different.
So the bouncer takes the fingerprint of the code trying to run. What does he compare it to?
He compares it to a golden signature. This signature is permanently physically locked into a highly secure, read-only area of the chip called the user configuration block, or UCB, back at the factory.
And if the newly calculated fingerprint doesn't perfectly match the golden signature, say a tuner tried to upload a hacked file or a torn write scrambled the data.
If the hash doesn't match perfectly, the HSM bouncer acts with extreme prejudice. It completely denies the main CPU any access to the application memory. It permanently locks the entire system in the basic bootloader state.
Wow.
It kills the bad code at the source, starving it of processing power before a single high-voltage relay can close or a single tire can turn.
I love that. The bad code never even gets the chance to execute. It's stopped at the door. Okay, so let's say the code is completely healthy. It passes the HSM fingerprint check. The bouncer lets it in. We move to layer 2, which is the U0311 dynamic handshake. What is this layer doing?
Well, just because the motor controller software is healthy and uncorrupted doesn't mean it plays nicely with the other computers on the network. Remember the communication drift problem, the out-of-sync dictionaries.
Right. We have to make sure they are all speaking the exact same dialect.
Exactly. So, after this secure boot passes, but before the car is allowed to close the main high-voltage relays.
And these are the heavy mechanical switches that actually physically connect the massive 800-volt battery pack to the drive motors, right?
Yes. Before those close, the network performs a rapid-fire interrogation. Within a tiny 20-millisecond window, they execute a 3-round, encrypted version token handshake.
It sounds like a spy movie. 3 agents meet in an alley and exchange encrypted passphrases before anyone is allowed to open the briefcase with the money.
That's exactly what it is. The VCU sends a challenge token to the motor controller. The motor controller decrypts it, adds its own specific software and physical calibration version data, encrypts it again, and sends it to the battery management system.
Oh, wow.
They are trading these cryptographic tokens that represent their exact, specific software realities. The master software then decrypts and compares all 3 tokens against an expected mapping.
And if any single token misaligns, even by a single character.
If it misaligns, the system immediately throws the U0311 diagnostic fault.
And what happens to the briefcase? The high-voltage relays?
They stay open. The car remains physically electrically safe because the high voltage is physically isolated from the motors. The system refuses to arm the weapon, so to speak. No handshake, no high voltage.
Incredible. Okay, let's talk about layer 3, AD bank flash and auto rollback. Here's where it gets really interesting, because this addresses a fear I think everyone has. Anyone who has ever stared at their phone while it sits on the Apple logo during an update, holding their breath, knows the fear of bricking a device.
Yes, bricking. When a device is bricked, the software has become so corrupted during an update that the device can't even boot up enough to accept a new fixed update. It is essentially a very expensive inert brick of glass and metal.
Yeah, and it's annoying if it's a $1,000 phone. You take it to the store.
But you absolutely fundamentally cannot allow a $50,000 electric vehicle to brick itself in a customer's driveway during an over-the-air update. You can't ask the customer to tow their immobilized car to a dealership just because the 12-volt battery sagged.
So how do they prevent that? The document talks about 2 memory banks.
The controller's physical brain, the flash memory, is strictly partitioned into 2 physically independent spaces. Bank A, which is the primary bank, and Bank B, which is the backup bank.
Okay.
Let's say you are driving your EV to work on Monday. The car is running on the software in Bank A. Everything is great. The software is proven and stable. Monday night, you park in your garage, and the car downloads a massive new firmware update over the Wi-Fi.
Okay, the update begins.
When it starts installing that update, it never, ever touches Bank A. It writes the new, unproven, potentially dangerous software entirely into Bank B.
So the old working software is still perfectly intact, sitting completely isolated.
Exactly. After the massive write operation to Bank B is finished, the system runs those heavy SHA-256 cryptographic hashes and the ECC integrity checks on Bank B to make sure it wrote correctly. Let's say it failed. Let's say a coolant pump kicked on, the 12-volt battery sagged, and it caused a massive torn right in Bank B.
The spell checker throws its hands up.
The system detects the failure instantly. And here's the magic part. Built into the hardware is a mechanism called the boot pointer. It essentially tells the processor where to look for instructions when it wakes up.
Mhm.
If the update to Bank B fails, the system automatically redirects that boot pointer right back to the healthy, untouched Bank A.
It just shrugs off the corrupted update, points back to the good software, and says, never mind, that was a disaster. We'll just stick with what we know it works.
Yes, it executes an automatic, totally seamless version rollback. When you wake up on Tuesday morning and get in your car, it boots up perfectly on the old software.
That's amazing.
And it silently sends a data log to the manufacturer's cloud saying, hey, that OTA update failed due to a voltage drop, schedule it to try again later tonight. You, the driver, never even know what happened. And more importantly, the car never bricks. It is self-healing.
That is brilliant engineering. It completely removes the anxiety from pushing code to thousands of cars remotely. But this brings us to layer 4, which is the ASIL D adaptive fallback. This is what we might call the so what protocol. If the system's defenses catch a failure, what does the car actually do in physical space?
It entirely depends on when it catches the failure. If it catches the version mismatched during startup, like while you're parked through the secure boot or that spy movie handshake, it executes what is called a gating lock.
A gating lock.
It absolutely refuses to send the electronic command to close the high-voltage relays. The high-voltage battery remains physically, mechanically isolated from the inverter box. The car is effectively inert. You will get a warning on the screen, but you are perfectly safe.
Which makes total sense when you're parked in the driveway. But wait, I have a massive question here.
Go ahead.
Let's say I'm driving. I'm already on the interstate, doing 70 miles per hour, surrounded by semi-trucks. If I'm understanding this right, if the software somehow gets corrupted mid-drive, maybe a cosmic ray flips a critical bit, or massive electromagnetic interference scrambles the RAM, shouldn't the system just instantly cut the power to be safe?
You mean just turn off?
Yeah, like instantly drop the high-voltage relays, disconnect the battery, and turn the motor off. Just pull the plug.
No, absolutely, categorically not. And this is a critical life and death safety distinction in EV engineering. What you were describing is called STO, or safe torque off. It is the go-to safety mechanism for factory robots.
Oh, right.
If a robot arm malfunctions, you drop the power and it freezes. But a car is not a stationary factory robot. It is a 2-ton mass of kinetic energy moving at high speed. If you instantly execute safe torque off and cut power to the drive wheels of a heavy EV traveling at highway speeds, you create a massive sudden loss of forward momentum.
Oh, because EVs use the motors to brake. Regenerative braking.
Exactly. The motor is deeply tied to the physical resistance of the wheels. If you instantly kill the inverter, you lose all controlled regenerative braking. But worse, sudden torque loss causes a massive, violent transfer of vehicle weight from the rear to the front.
The nosedive.
Yes. Now imagine you're going 70 miles per hour around a sweeping curve or driving in heavy rain. Abruptly cutting the motor torque alters the friction circle of the tires. You can easily cause the tires to lose traction. You could instantly spin out into a wall.
Yikes.
Or the driver behind you, who isn't expecting you to suddenly lose all forward power and decelerate rapidly without your brake lights fully engaging, could rear-end you at highway speeds.
So executing safe torque off on the highway is actually incredibly dangerous. It turns a software glitch into a physical pileup.
Precisely. So instead of a hard shutoff, the ASIL D protocol dictates a deeply complex limp home mode. It is all about graceful degradation. The system knows the software is corrupted, so it doesn't trust it to give full power. It immediately overrides the driver's pedal and limits the motor's peak torque output to under 30% of its normal rating, and it forces a strict hard speed limit of 40 kilometers per hour.
It smooths out the failure. It puts the car on a tight leash.
Yes, it prevents a catastrophic loss of control, it prevents sudden weight transfer that causes spinouts, and it prevents rear-end collisions by slowing down predictably. But it still heavily restricts the car's capabilities to prevent the corrupted, mismatched software from doing something insane, like commanding maximum acceleration.
Right.
It gives you, the driver, a safe, predictable, powered buffer to calmly steer the car over to the shoulder of the highway.
It's fascinating how the software engineers have to deeply understand the physical dynamics of a 2-ton vehicle at highway speeds. It's not just logic, it's physics, it's momentum. Which transitions us perfectly into our next phase of understanding, which is DFMEA.
DFMEA, Design Failure Mode and Effects Analysis.
Right. We spent a lot of time talking about how the system acts when things go wrong, how it catches the bad hash, how it limits torque, how it rolls back the memory. But now we're zooming out. We're looking at how engineers design the hardware and software architecture in the very first place to prevent these things from ever occurring.
Exactly.
It's like anticipating a massive earthquake and designing the blueprint of a skyscraper to absorb it, rather than just building a good fire alarm.
That's a perfect analogy. In the
Hmm.
design phase, you don't just hope for the best. You mathematically assume that everything will go wrong. You assume the battery will sag. You assume the mechanics will make mistakes. You assume the cosmic rays will hit. And you build physical and structural barricades into the foundational design to neutralize those threats before they ever manifest. We call these design prevention controls.
Let's look at the first one on the list, physical dual bank isolation. Now, we just talked about Bank A and Bank B for the OTA updates, but this design control explicitly states that they aren't just logical partitions. What does that mean?
It's a crucial distinction. If you partition your laptop's hard drive into a C drive and a D drive, they look separate on your screen. But physically, they're still living on the exact same spinning magnetic disk or the exact same silicon chip.
Okay.
If a bad enough electrical fault hits that chip, or if a severe memory leak overwrites the boundaries, it could easily wipe both the C drive and the D drive simultaneously. The illusion of safety is shattered by physical reality.
Right, they're just folders in the same physical filing cabinet. If the
Mm,
cabinet burns down, both folders are gone.
Precisely. To prevent this, the EV design specification mandates the use of microprocessors that feature physical active-to-active dual bank flash.
Meaning Bank A and Bank B are completely separate pieces of silicon real estate.
Yes, they are physically distant from each other on the die. They have completely separate, physically isolated decoding circuits, separate power traces, and separate data routing pathways.
Wow.
When the controller is writing a massive update to Bank B, the physical hardware logic makes it impossible for that write command, or the high voltage required to push those electrons, to bleed over and erode the floating gate transistors in Bank A. The backup version has absolute physical robustness.
It's like having your backup servers in a completely different city on a different power grid. Okay, the next design prevention is redundant boot headers. We talked earlier about the golden signature, the fingerprint that the bouncer checks being permanently stored in the UCB, the user configuration block. But what happens if a cosmic ray, a neutron, hits the UCB itself and scrambles the golden signature? Doesn't the bouncer just lock the doors forever?
That is the exact nightmare scenario this design prevents. The UCB contains the boot mode headers. These are the absolute most fundamental instructions that tell the silicon chip exactly how to wake up and start executing logic. To prevent a single point of failure from permanently breaking the chip, the design architecture mandates a mirrored redundancy.
A mirror.
Yeah, there's the original boot header block, and located elsewhere on the chip is a symmetrically placed, mathematically identical copy.
A twin.
Yes. As the chip wakes up, hardware-level logic checks the integrity of the original header. If it detects that the original header was corrupted by a soft error, like our cosmic ray, the hardware logic doesn't panic. It doesn't freeze or lock up. It physically switches a multiplexer over to read from the untouched copy, allowing the system to boot safely and preventing a total deadlock.
It is just layer upon layer of absolute paranoia, and I love it. Now, what about the communication drift problem? The dictionary getting out of sync between the battery brain and the motor brain, where 2 becomes an 8. The outline mentions something called a compatibility signature block. How does a software design choice permanently fix human error?
By taking the human being entirely out of the loop. In the old days of automotive software, an engineer might be working on the VCU code. They might manually tweak a single field in the communication matrix to fix a tiny bug, but they forget to manually update the overall version number in the documentation.
So they ship a changed dictionary but label it as the old version.
Exactly, and that stealthy change causes the mismatch down the line. To completely stop this, the new design architecture mandates a read-only binary hash block deeply embedded within the communication matrix code itself.
A binary hash block, explain that.
It's a mathematical summary of the entire dictionary. The engineers don't write the version number anymore. Instead, every single time the software engineering team compiles the communication code, like every time they hit the button to finalize a build, the compiler software itself analyzes every single signal, every data length, every scaling factor in the entire matrix, and it automatically generates a unique polynomial hash based on that exact data.
Oh, that's smart.
This hash is then permanently embedded into the code, as the true version signature.
So if an engineer tweaks even one single bit of data in the dictionary, they literally cannot compile the software without that hash changing automatically.
Exactly. It forces a 100% visible update. It physically and mathematically removes the capability for a human to make a stealthy, undocumented change. When the computers do their spy movie handshake later, they are trading these automatically generated hashes, ensuring absolute mathematical alignment.
Okay, this last design prevention is arguably my favorite because it solves the torn right problem so elegantly. It's
Right.
called brownout, hard block, and wear leveling.
If we connect this to the bigger picture, we spent a lot of time discussing how a dip in the 12-volt battery caused by a heavy coolant pump causes those nasty, incomplete memory writes that shred the code at the electron level.
Right. The light's dimming while you write the letter.
Now, a lazy engineering approach would be to write complex software to monitor the voltage, and if the software sees the voltage dropping, it tries to pause the update.
Makes sense?
But software is far too slow, and if the voltage drops fast enough, the software itself will crash before it can pause the write. So the architects solve a physical-electrical problem with a physical hardware solution.
A physical wire.
Yes. Designed directly onto the printed circuit board is a highly precision, analog, low-voltage monitoring circuit. It is constantly watching the voltage rails feeding the processor. If the 5-volt or 3.3-volt supply rails drop below exactly 4.5 volts or 3.0 volts respectively, this analog circuit instantly triggers a physical wire connected directly to the microcontroller's hardware reset pin
It literally pulls the plug on the brain.
in a matter of microseconds. It strips the electrical permission, the write-enable signal, away from the flash memory instantly. The write operation is physically blocked from continuing while the voltage is too low to sustain a healthy write. It is a brute force analog hardware block that completely eliminates the physical possibility of a torn write.
It's like a dead man switch for the software update. If the power sags even a fraction, the switch trips, the writing stops instantly, and the system waits to reboot from the backup bank. Brilliant. But what about the wear leveling part?
We have to remember that flash memory is a physical medium that degrades over time.
Mm-hmm.
Every single time you push electrons into those microscopic cages to write data
Yeah.
and then pull them out to erase it, you are physically damaging the microscopic insulating oxide layer inside the chip just a little bit.
It wears out, like bending a piece of metal back and forth until it snaps.
Exactly. If the software just wrote every new update to the exact same physical spot on the chip every time, that specific spot would burn out and fail after a few years, ruining the whole controller. To prevent this, the firmware design includes a wear leveling algorithm. It treats the massive memory bank like a giant chessboard. It constantly and invisibly shuffles the data around, moving blocks of code to different physical locations, making sure all the memory cells across the entire chip are used evenly.
Spreading the physical load so no single transistor takes all the damage.
Yes. By enforcing this design, the specification mathematically guarantees that the memory can endure at least 100,000 extreme erase and write cycles and guarantees the data will be securely retained without fading for 20 years.
So the engineers have designed this incredibly robust, self-healing, paranoia-driven digital fortress on their whiteboards. But a perfectly designed blueprint only matters if you actually build it correctly in the real world. Which takes us out of the pristine laboratory and into segment 4, PFMEA.
PFMEA stands for Process Failure Mode and Effects Analysis. This is where the rubber meets the road. We are leaving the quiet, theoretical world of software architects and stepping onto the loud, messy, fast-paced, high-pressure factory floor.
Right, because even the most perfect, cryptographically secure design can be completely ruined by a simple manufacturing error. You have a tired factory worker at the end of a 12-hour shift. Somebody picks up the wrong barcode scanner, somebody clicks the wrong drop-down menu on a dusty factory PC, and suddenly the physical car on the assembly line gets flashed with the wrong software brain. How does the factory stop that?
Through aggressive, unbypassable manufacturing process controls. The first major control is the MES flash checksum lockout. MES is the manufacturing execution system. It is essentially the master cloud brain that oversees the entire factory floor in real time.
Okay, the eye in the sky.
When a freshly built blank motor controller arrives at the flashing station on the assembly line, a robotic arm plugs a high-speed data cable into it to inject the software. But it doesn't just blindly dump the code from a local hard drive.
What does it do first?
First, the flashing machine reads the unique ID, the UID, which is a serial number physically baked into the silicon of that specific controller. Then it flashes the software. After flashing, it reads the SHA-256 hash of the software it just wrote.
The bouncer's fingerprint again?
Yes, the flashing machine takes that physical silicon UID and that newly written software fingerprint, and it sends them both up to the MES cloud. The cloud checks its massive global database. It says, okay, this specific physical motor controller, UID 1234, is destined to be installed into a high-performance, dual-motor EV being shipped to Europe. Does this software fingerprint precisely match the exact authorized European high-performance software build?
And if it doesn't match? Say the factory worker accidentally loaded the firmware for a standard range, single-motor domestic model into the flashing machine.
This is the critical physical intervention. If it doesn't match, the factory system doesn't just flash a red warning light on a computer screen that a busy worker might ignore or click past.
Yeah.
The physical factory fixture, the actual metal rig holding the controller, locks down. It interlocks.
It locks down.
It flat out refuses to actuate the printer, to print the physical barcode label that the controller absolutely must have to move down the conveyor belt to the next station.
Wow. It physically holds the hardware hostage.
Exactly. The process is broken. A manager has to come over with a key card, the controller is scrapped or reformatted, and the root cause is investigated. No bad software can physically leave that workstation. It completely eliminates human error from the flashing process by making the system enforce its own reality.
Okay, that handles the software. But what about the physical motors? We talked earlier about that terrifying scenario, the commutation offset learning, the fact that the software needs to learn exactly down to the micro degree, where the physical rotor magnets are to avoid blowing up the silicon carbide modules with 500 amps of overcurrent. How is that critical physical calibration handled safely on a moving assembly line?
Through a strict process called the EOL-RO lock, end-of-line rotor zero position learning. This is not an optional calibration. It is a mandatory, immovable step in the factory workflow. At the very end of the line, before the motor assembly is put into a car, it is bolted to a massive testing rig called a dynamometer.
A giant treadmill for motors.
Basically, yeah. The motor is spun up by the dynamometer under a very specific, carefully controlled microload. As it spins, the controller actively measures the resolver sensor, calculates its unique commutation offset, the exact magnetic fingerprint and alignment of its specific physical rotor, and securely writes that unique data into its permanent data flash memory.
It's literally learning the exact dimensions of its own body.
Yes. And if this test fails, maybe a sensor cable wasn't clicked in all the way or the memory write failed due to a glitch, the controller never successfully uploads that offset data back to the MES cloud.
And if the cloud doesn't see that offset data,
If the cloud doesn't see the data, it imposes a total system ban. When that motor eventually moves to the final quality testing booth where they try to run high voltage through it for the first time, the MES cloud actively bans that specific controller from ever closing its internal high voltage relays.
it effectively paralyzes the unit. It starves it of high voltage before it even has the chance to blow itself up.
Precisely. It is a 100% factory-level block of a zero-position mismatch.
Now, this last factory control, when I was reading the source document, this absolutely blew my mind. I had to read it 3 times. It says 3D X-ray, or AXI, solder check. Wait, hold on. You're reading from a software specification document, a document about coding and version mismatches, but it's demanding 3D X-rays of metal.
Yeah, it's wild.
That makes 0 sense. Software is code, X-rays are for broken bones and checking metal welds. How on earth did those get into the same engineering spec?
I know it sounds like a complete contradiction, but it perfectly illustrates how deeply physical real-world software actually is. We have to look at how the microcontroller chip, the brain running the code, is actually attached to the green printed circuit board.
Okay.
In high-performance automotive computers, they don't use chips with little metal legs that get soldered into holes. They use something called a ball grid array, or BGA.
Okay, what is a ball grid array?
Instead of legs on the outside, the entire bottom flat surface of the silicon chip is covered in hundreds of tiny, microscopic balls of solid solder.
Like a grid of tiny metal beads.
Exactly. The chip is placed onto the circuit board and the whole assembly goes into a massive reflow oven. The heat melts all hundreds of those microscopic solder balls simultaneously, fusing the chip flush to the board and creating hundreds of electrical data connections at once.
Okay, sounds like a standard, highly efficient way to build a computer.
It is. But melting metal isn't perfect. Sometimes, microscopic bubbles of air get trapped inside the liquid solder as it cools and hardens. These trapped air bubbles are called voids. Now think about the incredibly violent environment of an EV motor controller.
All right.
It is bolted directly to a metal chassis near a spinning motor. It is enduring massive thermal shock, going from freezing cold on a winter morning in Minnesota to boiling hot under heavy acceleration load an hour later. And it is enduring constant, brutal physical vibration from the road and the motor.
Shake and bake.
Exactly. If there is a void, an air bubble, hitting inside one of those microscopic solder balls, it creates a structural weak point. Over thousands of miles of driving, that thermal expansion and vibration will cause the metal around the bubble to stress and crack. Eventually, the crack propagates all the way through the solder ball, and the physical electrical connection breaks.
A broken wire.
But it's a microscopic broken wire hidden underneath a chip on a high-speed data line between the main processor and the flash memory. So as you're driving over a bumpy road, the vibration causes the two jagged ends of that cracked solder ball to rapidly connect and disconnect, thousands of times a second. It creates a microsecond transient electrical fault on the data line.
Into the software. What does that look like?
To the software, it looks exactly like a corrupted memory cell. The processor tries to read the memory, the physical connection breaks for a microsecond, the data gets scrambled in transit, and it looks exactly like a torn write or a massive version mismatch.
Oh, wow.
The software will immediately throw the U0301 fault, trigger the 40km/h limp home mode on the highway, and log a critical software error in the system.
Oh my God, and the mechanics at the dealership will pull the log, see a software error, and try to reflash the car.
They will reflash it, and the software engineers back at headquarters will spend weeks analyzing the code, tearing their hair out, completely baffled, because the software code is mathematically perfect. The problem isn't software. The problem is a microscopic bubble of air in a piece of metal hiding underneath a chip.
That is incredible. The hardware failure perfectly masquerades as a software mismatch.
Which is exactly why the software specification document steps out of the digital realm and mandates a physical process. It demands that 100% of these chips must be scanned with 3D automated X-ray inspection, AXI, or high-resolution ultrasonic testing on the factory floor immediately after the oven.
Because you can't see the solder balls with a camera. They were hidden under the chip. You have to look through the silicon. And what are the tolerances? How strict are they?
Extremely strict. The factory computer analyzes the X-ray image of every single solder ball. The total voiding area, the total amount of trapped air under the entire chip, must be less than or equal to 5%. And a single individual solder ball cannot have a void larger than 1% of its specific volume.
So they are aggressively, obsessively scanning for microscopic air bubbles on day one to prevent phantom software crashes and highway limp home events 5 years down the road.
It brilliantly bridges the physical and the digital in such a tangible way. You cannot have reliable software without microscopically perfect hardware.
Which perfectly sets the stage for our final section. We have the flawless design, we have the X-rayed, barcode-locked factory floor. But before they start mass producing hundreds of thousands of these controllers, they have to prove that it all actually works. Which leads us into segment 5, the BPNR, the validation phase.
Design verification plan and report. This is the crucible. This is where they take all of this brilliant design, all of these factory controls, and they hand the physical hardware over to a team of engineers whose entire job is to try their absolute hardest to break it, to destroy it, to trick it before it ever goes into mass production.
The torture tests. We're going to dive deep into 3 extreme tests outlined in the source document. Test 1 is called the critical OTA kill. This sounds exactly like what it is.
It is the ultimate brutal test of the dual bank memory architecture and that physical brownout protection wire we discussed earlier. They set up the controller in a lab and initiate a massive, complex, over-the-air software update. They are monitoring the exact byte-by-byte progress of the new data being written into the backup bank B.
Okay, the progress bar is moving, 10%, 20%.
And at exactly 50% completion, which is mathematically the most vulnerable critical phase, where the system is deepest into erasing and writing millions of flash memory cells, they literally pull the plug. They sever the main 12-volt power line, instantly plunging the system into a severe, instantaneous brownout.
They intentionally cause a massive torn write. They inflict the exact wound the system is designed to fear most. What has to happen next for it to pass?
They restore the power and turn the system back on. The acceptance criteria are brutal and unforgiving. The system must wake up. The bootloader must immediately run its HSM cryptographic hash check, and it must independently detect the massively corrupted Bank B code 100% of the time without the code crashing, freezing, or locking up the processor.
And then it has to execute the auto rollback.
Yeah,
Right.
yes.
Huh.
Upon mathematically proving the torn write via the failed hash, the system hardware must automatically redirect the boot pointer back to the completely healthy Bank A. And it must execute this entire sequence: wake up, cryptographic hash, failure detection, boot pointer switch, and full reboot in under 500 milliseconds.
Less than half a second.
Less than half a second from the moment power returns to being fully functional on the backup software. Oh, and it must flawlessly reestablish the spy movie handshake with the other computers, proving it is healthy, and be completely ready to try the update again.
That is incredibly robust. It proves that self-healing actually works in the worst-case scenario. Okay, test 2, shake and bake, or formally the data retention test. This goes right back to the X-rays, the solder bubbles, and the physical degradation of the memory cells. How extreme is this test?
It is punishing. It is designed to simulate 20 years of the worst possible driving conditions compressed into a few weeks. They take the fully assembled, perfectly functioning controller and put it into a massive environmental testing chamber. They rapidly, aggressively cycle the ambient temperature from -40 degrees Celsius, deep freezing winter where metals contract, straight up to positive 125 degrees Celsius, which is hotter than boiling water, where metals expand.
So violently expanding and contracting the
Yeah.
metal in the circuit board.
Yes. And while doing that thermal cycling, they mount the entire unit to a hydraulic shaker table and hit it with 3-axis random vibrations at an intensity of 35 meters per second squared.
Wait, let's do the math on that. 35 meters per second squared. Normal gravity pulling us down right now is 9.8, so that's almost 4 Gs of force.
Nearly 4 Gs of violent, random, multi-directional physical vibration, simulating driving over the worst possible pothole-ridden, frozen dirt roads while bolted directly to a vibrating high-torque motor.
That's insane.
And they don't just leave it there to shake. While it is violently shaking and boiling, they power it up under a heavy electrical load, and they continuously read and write massive blocks of data to the flash memory for over 1,000 continuous hours.
Over 40 days of continuous, violent thermal and electrical torture. What possibly counts as a pass after that?
0 bits lost. At the end of the 1,000 hours, they power it down, let it cool, and read the cryptographic hashes. The CRC, the cyclic redundancy check, must be 100% correct. Every single one and 0 out of millions must be perfectly intact in the floating gate transistors. And it doesn't end there. After it passes the software check, they perform a DPA, a destructive physical analysis.
Destructive, they break it.
They literally cut the controller apart with a precision diamond saw. They extract the microchips and the solder joints, put them under a scanning electron microscope, and physically verify that there are absolutely 0 fatigue microcracks propagating through the solder balls or the silicon die.
So if it survives 40 days of 4G vibration at boiling temperatures without a single microscopic crack or a single dropped bit, it can probably survive a trip to the grocery store for the next 10 years?
Exactly. It proves the physical baseline.
All right, the final torture test, test 3. The HIL 12,000 RPM fault injection. This sounds like the most cinematic test of them all. This is where they test the limp home mode, right?
Yes. HIL stands for hardware in the loop. You can't safely test these extreme high-speed dynamic failures on a physical test track with a human test driver. It is far too dangerous to intentionally corrupt the software of a car doing 70 miles per hour.
Yeah.
So they use a simulator. They bolt the real physical motor controller to a massive, high-fidelity FPGA supercomputer simulator in the lab.
Okay,
The supercomputer feeds the controller highly realistic electrical signals, tricking the controller's brain into thinking it's bolted into a real car, driving on a real highway, feeling real wind resistance and tire friction.
So the brain is sitting on a desk, but it genuinely believes it's cruising down the interstate.
Yes, they spin the simulated motor up to a screaming 12,000 RPM at absolute full load, meaning the driver has the pedal pinned to the floor, demanding maximum power. Then, while it's screaming at 12,000 RPM, the engineers use a custom fault injection card to execute a malicious cyber attack directly onto the data bus. They purposely corrupt the version token mid-drive.
They intentionally break the handshake. They simulate a sudden, massive communication database drift while the motor is at terminal velocity. What is the controller legally required to do to pass the test?
The requirements are incredibly tight because this is where lives are saved.
Yeah.
The system must instantly detect the corrupted token and mathematically realize that the software versions are no longer matching and cannot be trusted. It must trigger the ASIL D limp home mode in less than or equal to 100 milliseconds.
A tenth of a second.
In that single tenth of a second, while the simulated physical mass is screaming at 12,000 RPM, it must smoothly pull the requested motor torque down from 100% to 30%, and it must forcibly govern the simulated vehicle speed down to 40 kilometers per hour. And it must do this perfectly, mathematically, smoothly.
Right, because we talked about this. If it just jerks the power, the car spins out.
Exactly. The acceptance criteria strictly state, during this transition, there can be zero sudden torque spikes. There can be zero demagnetization currents, meaning no uncontrolled electrical backflow into the motor that could destroy the magnets. And there must be absolutely no simulated wheel lock. It has to reel in all that explosive, high-speed kinetic energy safely, smoothly, and instantly without upsetting the balance of the car.
It's like throwing a lasso around a speeding locomotive and bringing it to a controlled jog in a tenth of a second, using nothing but math.
That is exactly what it is. And it has to do it perfectly every single time.
So we have to pull all of this together. So what does this all mean? We started this entire journey talking about the simple, frictionless expectation of an Update Now button on a smartphone. We expect things to just work.
Right.
But what we've discovered over the last hour is an incredibly complex, violently physical world underneath that progress bar. We've seen how a single software update is protected by cryptographic handshakes that act like bouncers, by physically separated AB memory banks that absolutely refuse to let a car brick itself, by analog hardware wires that instantly pull the plug if the voltage drops, and even by automated 3D X-rays scanning for microscopic bubbles of air in factory solder to prevent a software crash.
It means that modern EVs are no longer just cars in the traditional sense. They are highly armored, self-healing, rolling data fortresses. The level of unseen engineering required to ensure your physical safety when algorithms meet 12,000 RPM is staggering.
It really is. The invisible safety nets are absolutely everywhere, woven into the metal and the code, catching the cosmic rays, the bad mechanics, and the torn rights before you, the driver, ever even notice a hiccup.
And the truly fascinating part is that they aren't stopping here. If we look toward the future, the very last engineering note in our source document leaves us with a truly provocative thought. The engineers who wrote this specification are already building the next generation of defenses.
What does that next generation even look like? Where do you go from X-rays and cryptography?
You go down to the quantum level. The document notes that advanced engineering teams are now using complex Python simulation models to calculate what they call flash floating gate charge decay and thermal resistance safety boundaries during those extreme voltage drops we talked about.
Okay, translate that. What does that mean?
It means they are no longer just looking at the circuit board. They are computationally simulating the precise quantum decay of individual electrons trapped inside those microscopic silicon cages under extreme heat and vibration.
Whoa.
They're trying to optimize exactly how many microseconds they have to save the data before the physical voltage fails and the electrons escape.
They are modeling the quantum decay of electrons to make a car software update safer.
Yes, it raises an incredible, almost philosophical question. As our vehicles become entirely software-defined, as the mechanical metal and the digital code become completely inseparable, will the mechanics of tomorrow need to understand the quantum behavior of electrons just to safely change a tire, replace a motor, or update an app? It is a merging of disciplines, mechanical engineering, computer science, and quantum physics, unlike anything we have ever seen before in consumer technology.
A mechanic standing in a service bay with a wrench in one hand and a quantum physics textbook in the other. That is an incredible image. And it's definitely something to think about the next time you sit in your driveway, look at the glowing screen on your dashboard, and casually tap Update Now.
Indeed, it is never, ever as simple as a progress bar.